everyone, welcome back to another video on my channel. Today we're going to be talking about another super interesting topic. This kind of relates to what I shared last week, but it kind of doesn't as well. So last week it was arithmetic sequences. This week, can you guess it? Well, I mean it's not easy to guess, but it is easy to guess. Don't mind me. It's geometric sequences. Let me write the title. Now, you can see that I've attached an image up here. And that image, if you read it, it said compound interest. Now, whether you've heard about compound interest or not is a different thing, but compound interest is something related to money. It's financial thing. So compound interest is one of the most majorly used examples of geometric sequences and series. Its finance involves so much of arithmetic and geometry, so if you wouldn't even realize it, you were just doing it almost every day. Right. And another example is a direct relation to biology, mitosis and meiosis. Now, mitosis is where each cell splits into two identical cells. Um, yeah, so it's basically each cell is doubling. So in this picture, if this one cell became two cells, and if we wanted to see really how this relates to geometric sequences, each of these two cells would become two more cells, making a total of four. Then you would have eight, two from each, right? Clearly geometric. However, meiosis is a little bit different. Meiosis, it stops right here. Because each of these cells, they're not identical to this original one. They have half the number of chromosomes as the original one. But that's biology stuff. Yeah. So as you saw, you might not even think about it, but you're using these kind of math topics in so many other fields that it just makes it directly interesting to learn about, right? Now, let me show you a simple example. I'm sure you would have all seen this before of a geometric sequence. Let's say 2, 4, 6, 8. Whoops, that's arithmetic. 2, 4, 8, 16, 32. Now, what is happening in the sequence? From 2, you multiply by 2 to get 4. Now, what if you added 2? You add 2, then here you add 6. Wait, you add 4, 6 here, or 8. Then you add 16. Well, this doesn't really look like an arithmetic sequence, right? Because you're not adding the same thing every time, so that's not right. Now, what if you multiplied by 2 instead? Aha! Now you can see that we're multiplying by 2 every single time. Times 2, times 2. There you go, that's our pattern in the sequence. So, in a geometric sequence, instead of adding or subtracting, you multiply or divide. And this number that you multiply or divide by is called the common ratio. In this case, 2 is the common ratio. So now if I were to say this term this sequence went on until 1024, how do you find any term in the sequence just by taking its term number? So if I asked you to find the first term, you'd say, well, yeah, it's easy. It's just 2. The second term, well, that's 4. Third term's right there, 8. Right? Fourth term, fourth term is 16. Yeah, so you can keep going because it's right there. However, what if I asked you to find the ninth term? I mean, you could just multiply every time by 2, but shouldn't there be an easier way to this? Or instead of 1024, how about 2048? Or actually, let's just keep it at 1000. I like this number. Yeah. So let's try to look for a better approach. Now, if you notice, each and every one of these terms are powers of 2. So let me write it like this. 2, the first term, I'm going to write term number 1 is 2 to the power 1, which is just 2. And term number 2 is 2 to the power 2, 2 squared, which is 4. Term number 3 is 2 to the power 3, which is 8. term number 4 is 2 to the power 4, which is 16. Now, clearly, for all the numbers we've written down, there seems to be a pattern like this. However, what if, what, you don't know if this would be true for the entire thing. So now let us try to actually find the ninth term using this pattern, right? So we think the ninth term is 2 to the power 9, correct? But is it? Let's prove that. Now, the trick here is just the same as what we did last time in arithmetic sequences, 2 videos ago. That would be this right here. To get to the ninth term, so I'm going to write the term number 9. To get to the ninth term, you start at 2, and then you multiply by 2 8 times. In other words, from the first term to get to the ninth term, you have to take 8 steps in between, right? So you have to multiply by 2 8 times. 2 times 1, 2, 3, 4, 5, 6, 7, 8, right? So this would give you the value of the ninth term. You start at the initial value and you multiply by the common ratio n minus 1 times to get to the nth term. Now, in this case, the common ratio and the starting term happen to be the same, but it's not always going to be the case. So 2 times 2 multiplied 8 times. Now this, in the parentheses, it just becomes 2 to the power 8, 2 times 2 to the power 8, and now simplifying that is 2 to the power 9. And there you go, the ninth term is indeed 2 to the power 9, and using the same logic, we can just multiply to get to the nth term. We just do 2 and 2. We can't write n times because we don't know what n is, so I'm going to write using this notation, and I'm just going to keep it going until 2 to the n, right? Simple. Then this becomes 2 times, oh, whoops, it's not n, it's n minus 1 terms. 2 times 2 to the power n minus 1. Then adding up the exponents, 2 to the power n. And that's the formula for our geometric sequence. Now, let's just take it a step directly and generalize this formula. Let's say the starting term is a. I'm going to write this as the starting term. R is the common ratio. Now, common ratio is a very important term. It's useful to remember this term. That's the common ratio, and that's pretty much all we need. Let's say there are n terms. Yeah. Number of terms. Then, how do you find the nth term? Or actually, why do we need this? This is not important. That would be like a giveaway, right? Yeah, so now, given the starting value and the common ratio, how do you find any term in the sequence? In other words, how are you going to find the nth term? Term number n. Let's see. We'll use the same trick as last time. Remember, there's nothing special if you change numbers to variables. Nothing special, same exact tricks. Now, we're going to do the same thing by starting off at a, and to go to the nth term, you have to take n minus 1 steps, right? So in each of the steps, you multiply by r. So you multiply by r n minus 1 times. In total, you multiply n minus 1 times, right? Then this becomes a times r to the power n minus 1, or generally you write it without this dot in the center and just ar to the n minus 1 power. And this is the ultimate magic formula for any term, for you to find any term in a geometric sequence, right? Cool. Now, let's use the mitosis example in the beginning. Let's say I start off with 4 cells, 4 different cells. I'm starting off with 4 different cells. Then after one procedure of meiosis, each cell splits into 2 cells, which means you're going to have double the number of cells, which is 8. Then after the second round of mitosis, you'll have 16. After the third round, you'll have 32. After the fourth, you'll have 64. And this will keep going. This is actually infinite. It never stops. It keeps producing cells to replace the dead ones and as you grow. So, yeah. All right. So now we're going to use the same thing, but this time we're going to find the 12th term, or let's say the 20th term. Yeah, let's just find the 20th term. Now, unlike an arithmetic sequence, geometric sequences tend to increase very fast. And I'm going to come to that in just 1 second to explain why, compared to an arithmetic sequence. Now, look at this carefully. Let's start at 4 to find, actually, instead of finding a random term, let's just find the nth term of the sequence. It generalizes, right? If you know how to find the nth term, you can find any term. So you start at 4, then you multiply by 2, n minus 1 times. So there's n minus 1 2's being multiplied right here. Then this becomes 4 times 2 to the power n minus 1. Now you think, okay, this is the furthest we can simplify it, right? But before you jump to conclusions, look at this interesting fact. 4 can be written as 2 squared. It's a power of 2. So then this just becomes 2 squared times 2 to the power n minus 1. And this in fact simplifies to 2 to the power n plus 1. And there you go. Simple. We've just found the formula for the nth term of the sequence, which means if you wanted to find the 20th term, you just have to plug in 20 for n and solve, and you'll get to 2 to the power 21. And just saying 2 to the power 21 is a pretty big number. It's not small. So we just went 20 terms ahead, yet we got a huge, huge, huge number. In fact, I'm going to admit I use a calculator to do this, but 2 to the power 21 is 2,097,152. Now, why did, in 21 terms, why did it become so big? Imagine if this was arithmetic and not geometric. If it was just 4, 8, and instead of 16, if it was 12. And then after that, if it was 16, and then 20. I mean, so instead of multiplying by 2, you add 4 each time. The 20th term would literally be, let me do this in my head. So from 4, you add 4, basically, to get it to 19 times. So then that's pretty much, that's just 20 times 4. The 20th term, and if it was arithmetic, would just be 80. 80. That's it. Compared to 2 million. Oh my God. Well, there has to be a reason this tiny little change is causing such a big deal, right? Well, let me quickly show you why. I'm going to switch to graph paper here for a second just to draw a quick graph. Now let's graph an arithmetic sequence. Actually, yeah. Let's graph an arithmetic sequence and see what it looks like. And trust me, after you've seen the graph of this, you'll be like, oh yeah, I've seen that before. It's just blank. I'm not revealing it yet. Now, let's say we had that sequence we were talking about, 4, 8, 12, 16, right? Let's say we had that. The formula for this, I'm just gonna do it right now. It would be the formula for this, actually, let's do this down here. So 4, from 4 you take n minus 1 steps of 4. So basically this is just 4n, right? That's simplifying. Anyway, so this is the formula. So for generally how we write to graph it would be t of n equals 4n. And now this is the same as writing f of x equals 4x, or just y equals 4x. I'm sure you're all familiar with this. Now this and that would give you the same graph, except it's different with sequences. I'll tell you why. For n, right? Now let's say we start off at 0, it's 0. If n is 1, this is n, and this axis here is t of n. If n is 1, 4 times 1 would give you 4. If n is 2, 4 times 2 would give you 8. If n is 3, 4 times 3 would give you 12. And you can already see what figure this forms, correct? You got it. It's a line, just a line. Simple. Now, let's say if I were to graph this sequence right here. The formula for this sequence, I'm going to change colors here. The formula for the sequence is 2 to the power n plus 1. So now, if n is 1, then 2 to the power of 1 plus 1, 2 to the power of 2 would be 4. So if n is, or let's start if n is 0. If n is 0, which means this is 0, then 2 to the power of 1 would be 2. Then if n is 1, which is right here, 2 to the power of 2 would be 4. If n is 3, 2 to the power of 3 would be 8. Now when n is 4, 2 to the power of 4, this time it's not 12. In fact, oof, we don't have space. 1, 2, 3, 4, 5, 6, wait, 12, 13, 14, 15, 16. It would be here. Don't mind these intersecting lines. Actually, let me try to deal with that. I'm just going to move this off to the side. So 16, that would be the value. Now, connecting this does not form a line. In fact, it's a curve. And these curves are what you call exponential functions. I'm trying to do my best to draw the curve here. It's clearly not easy. There. That's roughly it. So now as you can see, it starts off at a higher value, it goes to a lower value, and it goes slightly lower this line, then eventually it overtakes the line, it goes above it. Now that's because geometric sequences, its nature is to increase faster than an arithmetic sequence. So if you, in a bank account, if you were to choose versus simple and compound interest, you choose compound interest because over the years, over a long time, you'd have more money than if you chose simple interest. Now, that's not always the case. It is always the case for infinite years, but generally you don't put it forever in an account, right? You're going to take it out at some point, right? So here's the thing. Let's say this was our arithmetic sequence. This was our line, right? Now, this line has equation y equals 1/2 x. That's the equation of this line. Now, let's say we had an exponential function y equals 2 to the power x. Or actually, instead of y equals 1/2 x, let's just do x. It makes it much easier to see and understand this. So here you go. Here's the line. Whoops, that didn't come out right. Right, I'm gonna do this a little bit better. Okay, here's y equals x. That's the line. Now we're gonna graph y equals 2 to the power x. This is their equation, and if we're gonna do the same procedure as before, if x is 0, 2 to the power 0 starts off at 1. If x is 1, 2 to the power 1 is 2, right? Yeah. Well, now this is obviously going to be higher. Okay, let me do a huge example. Let's say it was x plus 5. Or no, let's do 8. Sorry, I keep changing this a lot. It's just to make it look, show you really clearly why some things happen. Okay, so here's the y equals x. Actually, let's keep it at 6. I'm going to keep it at 6 here. So 6. All right, this is good. Okay, here's our line, y equals x plus 6. Now, as you can see, the exponential function starts off lower than the linear function, right? Now, in this case, the linear function is an arithmetic sequence and the exponential function is a geometric sequence. So now let's keep plotting this exponential function. When x is 2, 2 to the power 2 is 4. So that's, now this directly skips up there. In a line, if it goes one up, it would go here and here and here to form the line. But in an exponential function, it's different. Now, if x is 3, y would be 8, and that jumps. Oh, wow, that's a pretty big jump. Jumps all the way up there. Now, if x is 4, y is 16. And that point is up there. So you can see how high this actually is. And look how fast this graph is growing compared to this lame exponential function. Now, if this was a bank account and if I were to ask for my money back after 2 years, then at 2 years in time, this would be my point in time on this graph. And at this time, the linear function is higher than the exponential function. So I would choose simple interest. But let's say I wanted it after 4 years. 4 would be this point right here. And this would be the time when I would take out the money for my account. Now, this point, just 2 years ahead, the exponential function is so big. It's way larger than this linear function. So for after 4 years, I would choose compound interest. It's just like that. So that was the basic idea of arithmetic and geometric sequences. Thank you so much for watching this video. I really hope you enjoyed it. It was a little long, but it is extremely interesting and important. Thank you so much for watching. Please subscribe to my channel and hit a huge like on this video.